What would you see if you could watch time itself die? Imagine standing on the edge of the universe, where the ticking of every clock slows to silence, where the rhythm of existence itself begins to fade. That is not poetry, but physics, written into the geometry of space-time. Time does not flow the same for everyone. It bends, it stretches, it hesitates in the presence of gravity. And the deeper one goes into a gravitational well, the slower that cosmic heartbeat becomes, until at last, it nearly stops. We live our lives assuming time is absolute, that 1 second for you is 1 second for me. Yet Einstein showed otherwise. Time is not a universal pulse, but a local one, set by the gravity of your surroundings. At sea level, where Earth's pull is strongest, time moves imperceptibly slower than it does atop a mountain. The difference is minute, barely a few billionths of a second each day. But it exists. Our satellites, the silent sentinels orbiting above us, feel that difference. The atomic clocks aboard global positioning satellites tick faster than those on the ground. Engineers must adjust them continuously. Without that correction, GPS systems would drift by kilometers each day. In the machinery of modern civilization, relativity is not an abstraction. It is a calibration. Now imagine extending this difference beyond the realm of the everyday. Picture two observers, one standing far from any massive body and another hovering close to something dense and immense, perhaps a neutron star. For the observer near that star, gravity's pull distorts space-time so profoundly that their seconds lengthen. To the distant observer, their clock appears to slow, their heartbeat to fade. This is gravitational time dilation, not an illusion, but a deep truth of the universe. Gravity stretches the fabric of time itself. Every planet, every star, every cluster of galaxies sculpts the flow of time around it. The stronger the gravity, the slower time runs. On Earth, the difference between mountaintop and valley is trivial. Near a black hole, it becomes absolute. As one approaches the event horizon, the warping grows infinite. From far away, it seems that any clock falling toward the horizon slows forever, never quite reaching it. The fall is eternal from our perspective, yet instantaneous from the falling traveler's own view. Time fractures into two realities, each valid, each irreconcilable. It is here, at this frontier, that the concept of a gravity horizon arises. It is not merely a place where light cannot escape. It is where the structure of time itself breaks down from the outside view. The horizon is the ultimate expression of relativity, the boundary where time for the distant universe halts, frozen at the edge of infinity. This idea invites a question older than science itself. If time can slow, can it ever truly stop? Could there be a place where the very idea of before and after ceases to exist? An object's final approach drawn out endlessly, its image forever dimming but never vanishing. For the external cosmos, the infalling matter seems paused in an eternal farewell. Yet from within its own frame, time flows as naturally as ever. The traveler falls, crosses the horizon, and continues, unknowing that for the rest of the universe, they have already become history. To reach such extremes of time, we must first understand what gravity truly is. For centuries, humanity imagined it as a force, an invisible thread binding masses together across the void. But Einstein revealed a deeper truth. Gravity is not a force acting across space. It is the shape of space itself. Matter tells space-time how to curve, and space-time tells matter how to move. This idea changed everything. Our picture of the cosmos, of motion, of time. Consider a simple analogy. Imagine stretching a rubber sheet taut and placing a heavy sphere upon it. The sheet dips, and any smaller ball rolling nearby spirals inward, not because the larger ball pulls it, but because the surface guides its motion. Replace the rubber with space-time, the sheet with geometry itself, and you glimpse Einstein's universe. Planets orbit stars because space around the star is curved. Light bends around galaxies because space-time itself is warped by their mass. Gravity is geometry. The same curvature that bends paths through space also bends paths through time. Near a massive body, time runs more slowly because space-time there is stretched in the temporal direction. What we perceive as the pull of gravity is our natural motion through curved time. This is why astronauts orbiting Earth feel weightless. They are simply following the natural curve of space-time, moving freely through its geometry. The sensation of gravity we feel on the ground is not a force pushing us down, but the ground pushing up against the straight line our bodies would otherwise follow through space-time. All of this becomes critical when we imagine what happens as mass grows and density increases. Compress a star beyond its limits, and the curvature intensifies without bound. The point at which time dilation becomes infinite defines a threshold, the Schwarzschild radius. It marks the event horizon, the surface from which not even light can escape. At that radius, space and time are warped to their extremes, forming the border between the knowable and the unknowable. In mathematical form, this relationship can be written in the Schwarzschild metric, which describes how space-time behaves around a spherical mass. The ticking of a clock at a distance r from a mass m is slowed by a factor depending on how close it is to that mass. As r approaches 2 times the gravitational constant g multiplied by the mass and divided by the square of the speed of light, the flow of time approaches 0. No real clock ever stops from its own point of view, but to the universe beyond, it freezes at the brink. This is not imagination. It is built into the geometry itself. Thus, the edge of time is not a place in space. It is a boundary of perception, a horizon separating 2 versions of reality. One where time flows on, and one where it stands still. The gravity horizon is the most perfect mirror the universe has ever made, reflecting not light, but the limits of understanding itself. And so, as we stare into the mouth of a black hole, we are not merely looking into darkness. We are watching the death of time as we know it. The laws of physics hold, but their meanings twist. The coordinates of space and time swap roles. The pace of clocks diverges, and what we call reality fractures into perspectives that can never meet. The question remains, what happens beyond that edge? To find the answer, we must step further into the heart of Einstein's vision, to see how the fabric of reality bends, not just space, but the rhythm of existence itself. For only by understanding that curvature can we glimpse the full nature of the horizon, where the illusion of time begins to fail, and gravity becomes more than a force. It becomes the architecture of destiny. To understand why time slows in the presence of gravity, we must begin with a more intimate image. Imagine standing near a massive planet, perhaps a gas giant 10 times heavier than Earth. The ground beneath you presses with unimaginable force. Each photon of light climbing away from that planet loses energy, stretching into longer wavelengths. It is not because anything steals its power, but because time itself flows differently at your feet than it does far above. The same effect that reddens the light also stretches the seconds of your life. You age slower than those orbiting high above, though the difference is invisible to your senses. Yet in the language of relativity, that difference is absolute. The universe keeps 2 separate ledgers of time, and neither is wrong. Now shift your imagination to a region where gravity is not merely strong but extreme. A collapsing star, crushed by its own mass, curves space-time so sharply that the outward paths of light begin to tilt inward. Even photons that try to escape are slowed, bent, and delayed. Their journey grows longer and longer until the slope of time itself becomes vertical. For the distant observer, that final flash of light never truly departs. It lingers, stretched and dimmed, as though caught in the act of escaping forever. The star's image freezes. Its surface seems to hover, motionless, as if the cosmos has pressed pause. But for the star itself, for every atom and every quark within it, nothing unusual occurs. In its own frame of reference, it collapses in finite time, crossing a boundary unseen, moving onward toward the singularity that lies within. Both descriptions are true. Neither can reach the other. That is the strange democracy of relativity. Every observer's time is equally valid, yet none can claim to see the whole. When we speak of time slowing near a black hole, we must remember that this is not a trick of perspective, but a fundamental property of space-time curvature. Time, like space, is woven into that four-dimensional fabric. It does not flow independently, but is bent along with the geometry. The closer one approaches the center of mass, the deeper the well becomes, and the more the intervals between events stretch. Clocks do not break, nor do they malfunction. They merely follow the local rules set by the shape of space-time. Consider again the notion of escape velocity, the speed needed to break free from gravity. On Earth, it is about 11 kilometers per second. On a neutron star, it may exceed 100,000 kilometers per second. At the Schwarzschild radius, the escape velocity reaches the speed of light itself. Beyond that boundary, no signal can climb out, for light defines the fastest path through space-time. This boundary is the event horizon, the literal point of no return. To the outside universe, this horizon marks the end of time. Any process that occurs near it appears to slow endlessly, asymptotically approaching stillness. The final flash of a dying star lingers at the threshold, fading, but never crossing. The black hole's surface becomes a frozen record, a photographic negative of everything that ever fell within. Each moment is preserved, suspended in infinite time dilation. To the falling traveler, however, none of this is visible. They see no boundary, no wall of light or fire, no transition at all. They simply drift past the horizon and continue inward, as easily as you might walk through an open doorway. It is a duality that challenges the intuition of even the most experienced physicist. From one perspective, the horizon is an eternal surface where time stands still. From another, it is a fleeting coordinate, crossed in seconds. How can both be true? The answer lies in the relativity of simultaneity, the fact that events which are simultaneous for one observer may not be for another. Space-time itself allows these contradictions, because now has no universal meaning. This realization changes how we see the cosmos. The horizon is not a physical shell in space, but a feature of geometry. It divides the universe into regions defined by the paths light can take. Inside, all paths lead inward. Outside, some can still escape. It is this difference in the structure of light cones, the possible directions that signals can move, that defines what is possible and what is forbidden. To an external eye, time halts at the horizon because light from that region can never emerge again. For the traveler within, time flows normally because their light cones tilt inward, carrying them toward the future that ends in the singularity. Gravity does not simply warp space, it sculpts the rhythm of causality itself. The stronger the gravity, the more tilted the structure of time becomes, until the very distinction between up and forward in time dissolves. Near a black hole, space and time are entangled in a dance that no human experience can replicate. Every motion forward becomes a motion downward. Every attempt to hover becomes a battle against the flow of reality itself. When we look at a black hole through telescopes, we are not seeing an object, but a story told in slow motion. The light from the infalling gas is stretched, reddened, and delayed. The swirling disk glows fiercely, its inner edge tracing the boundary of eternity. Beyond that, there is no sight, no signal, only silence. The black hole's darkness is not absence, but culmination, the point where light, time, and meaning converge into stillness. And yet, this stillness is deceptive. For the infalling observer, time continues. The clock on their wrist ticks. their heartbeat echoes in rhythm. In their final moments before the singularity, they may even look outward and see the entire history of the universe sped up, as if the cosmos itself were rushing toward its own end. This reversal of perception is the ultimate consequence of time dilation. What appears frozen from one frame becomes accelerated from another. Thus, the horizon is not only a limit of motion, but a limit of understanding. It divides realities that can never communicate, each sealed within its own temporal flow. To study it is to confront the boundaries of human perception and the definition of time itself. And yet, to truly understand why this happens, we must dive deeper into the mathematics of space-time curvature, into the geometry that shapes not only motion, but existence. For if gravity can slow time to a halt, what does that say about the nature of reality beneath it? The universe does not hide its answers, it encodes them in geometry. To comprehend the horizon, we must think not of forces or fields, but of shapes. Einstein's equations tell us that space-time bends in response to mass and energy, and this bending dictates how time flows. Where curvature is mild, as near Earth, time only slows by a fraction. But where the curvature deepens beyond imagination, as near a black hole, the flow of time nearly halts. Every point in space-time has its own tempo. A clock floating far from any gravitational source ticks at what we call proper time, a rhythm unwarped by curvature. Bring that clock closer to a massive star, and each second stretches longer compared to the distant observers. The mathematical law governing this is contained in the Schwarzschild metric, which acts as a ruler for both space and time near a spherical mass. It shows that time slows as one approaches the Schwarzschild radius, the critical distance where gravity's pull becomes absolute. Beyond this radius, all possible paths through space-time curve inward. Light cannot escape because space-time itself funnels all motion toward the singularity. But what does that mean for time itself? For the external universe, any signal emitted from just above the horizon takes longer and longer to arrive. Each pulse is redshifted more strongly than the last, its wavelength stretching toward infinity. Eventually, the signal fades completely, as though the object has vanished into stillness. Yet in reality, the object continues its fall. Its proper time flows unbroken, but its story, as seen from outside, ends in slow motion. This paradox is not a failure of physics. It is the essence of relativity. There is no single absolute time that binds all perspectives. There are only local times, each valid in its own frame. The event horizon marks the point where these perspectives diverge infinitely. Beyond it, communication ceases. Inside, every direction becomes futureward, every possible world line drawn toward the singularity that ends all histories. Think for a moment of what this implies about causality. Outside the horizon, one can still choose directions: forward, backward, up, down. Inside, there is no such freedom. The geometry transforms so that the inward direction is as inevitable as the passage of time itself. No engine, no force, no wish can change that trajectory. To exist within the horizon is to move toward the singularity just as surely as we, here, move toward tomorrow. The singularity is not a place in space, but a point in time. It is the end of the story for every line that crosses the horizon. To the falling observer, it is not distant. It lies ahead, waiting like the next second of a clock. The entire future leads there, compressed into a single inevitable moment. And because no signal can return, no event within can influence the universe without. The interior of a black hole becomes a sealed region of space-time, its contents forever cut off from causality beyond. From this realization, the phrase "the edge of time" gains literal meaning. At the horizon, from the viewpoint of the cosmos, time stops advancing. No new moments are added to the record of that boundary. All that remains is a frozen imprint, an eternal now. For anything that crosses inward, time continues until it reaches the singularity where our laws of physics collapse. In that final instant, the distinction between space and time dissolves completely. This strange duality, frozen eternity from outside, relentless fall from inside, is one of nature's most profound riddles. It tells us that time is not a universal flow, but a relationship between observers. It depends on where you are and how gravity shapes your path. Near the horizon, the difference between those paths becomes infinite. To watch from afar is to see time arrested. To fall is to experience its unbroken continuity. In a sense, every black hole is a natural time machine, though not one we could ever return from. Its horizon separates two kinds of time: ours, which moves steadily onward, and its own, which turns inward, contracting toward a singular end. The universe outside sees the fall unfold forever, but the traveler experiences it as swift and final. Both realities coexist, neither complete without the other. As the equations describe it, the geometry of a black hole is deceptively simple. The Schwarzschild radius depends only on mass. Double the mass, and the radius doubles. Compress enough matter into a small enough region, and the horizon forms automatically. There is no special material, no exotic mechanism, only geometry responding to energy. Yet what emerges from that simplicity is one of the deepest mysteries in physics, a region where space, time, and causality themselves seem to unravel. And so we return to the opening question. What would you see if you could watch time itself die? You would see light stretching to infinity, color fading into black, motion slowing until it freezes. You would see the last heartbeat of a star captured forever on the surface of the horizon. But you would also know that inside that silence, time still flows, indifferent to your gaze. The death of time is not a destruction, but a transformation, a folding of reality upon itself. To understand what truly happens beyond that veil, we must go deeper still into the very structure of space-time. For gravity is not a force pulling on the fabric. It is the fabric's own curvature, guiding all that exists. In the next step, we will explore how this curvature arises, how the universe itself bends under the weight of its contents, and how the flow of time is written into that bending. Gravity, as we first learn it, feels like a force. It is the weight that holds us to the ground, the pull that guides a stone when released from the hand. Yet this old picture conceals a deeper truth. Gravity is not a pull at all. It is the shape of reality itself. Einstein's great insight, written in the language of general relativity, revealed that mass and energy tell space-time how to curve, and that curvature tells matter how to move. Imagine space-time not as emptiness, but as a vast, invisible fabric. Place a mass upon it, and the fabric dips. Smaller objects slide along the slopes of that curve, not because they are pulled, but because they are following the straightest possible paths through a bent landscape. The planets orbit the sun not through a cosmic tug, but through geometry. They trace ellipses because space and time themselves are curved around the solar mass. Yet the analogy of a stretched sheet is only a shadow of the real thing. The true bending of space-time occurs in 4 dimensions, where time joins the 3 dimensions of space. To picture this, imagine that every second of your life is another slice of a great 4-dimensional structure. You are not moving through time, you are extended within it. Gravity changes how these slices stack together. Near a massive body, the stacking becomes distorted, and that distortion changes both the geometry of space and the rhythm of time. The equations that describe this bending are known as Einstein's field equations. They relate the curvature of space-time, expressed through tensors, to the energy and momentum of whatever matter exists within it. The mathematics is dense, but its meaning is elegant. Matter and geometry are 2 sides of the same coin. There is no gravity field separate from space-time. Space-time itself is what gravity is. One of the simplest and most powerful solutions to these equations was discovered by Carl Schwarzschild in 1916, while serving on the front lines of the First World War. He found that for any spherical mass, there exists a precise mathematical description of space-time around it, the Schwarzschild metric. Within this geometry, the ticking of a clock and the shape of every path are governed by the same curved structure. Time runs slower near the mass because the geometry itself stretches intervals between events. Mathematically, if we compare a clock at a distance to one near a massive body, we find that as the distance shrinks toward the Schwarzschild radius, 2 times the gravitational constant multiplied by the mass, divided by the square of the speed of light, the difference in time flow becomes infinite. No observer at a safe distance will ever see that inner clock complete another tick. It is as though time, from that vantage, has frozen solid. Yet nothing physical stops the clock. To the traveler near the boundary, seconds pass as always. Their heartbeat continues. Their motion feels smooth. This contradiction arises because the coordinate we call time in the outer universe loses its meaning at that radius. The horizon marks not the death of a clock, but the death of a shared definition of time. The Schwarzschild metric also reveals how space itself stretches. Distances near a massive body are longer than they appear. If you could drop a measuring rod toward the horizon and count how many fit between 2 points, you would find that more rods are needed than in flat space. The curvature lengthens space, even as it slows time. Together, these distortions define the warping that we perceive as gravity. To see how deeply this connection runs, consider light itself. In a vacuum, light follows the straightest possible path, called a geodesic. When spacetime bends, these geodesics bend with it. Light passing near a star appears to curve because it is tracing the natural shape of the surrounding spacetime. When we measure this deflection during eclipses, we are watching geometry in action. The bending of light is not the bending of a beam through glass. It is the bending of reality. Such curvature does not only guide light and matter, it reshapes causality. When gravity grows strong enough, it changes what directions are possible within space-time. Outside a black hole, one may move freely in space or wait as time passes. At the horizon, those freedoms collapse into one. The direction of motion is drawn irresistibly inward, and forward in time becomes synonymous with falling deeper. The geometry commands it. This insight dissolves the old idea of gravity as an external force. There is no invisible hand pulling downward. Instead, what we call the pull of gravity is our resistance to spacetime's natural flow. When you stand on Earth, you are accelerating upward through the geometry, prevented from following the free-fall path that spacetime prescribes. Astronauts in orbit feel weightless because they are not resisting. They are simply moving along that natural curve. Everywhere in the universe, this same principle holds. Galaxies dance not because of unseen tethers, but because the shape of spacetime choreographs their motion. Clusters of galaxies bend the paths of light from more distant sources, creating cosmic mirages called gravitational lenses. These lenses magnify and distort the appearance of faraway galaxies, allowing astronomers to see deeper into the past. Through them, the curvature of spacetime itself becomes an instrument of observation. The universe, then, is not built upon a stage of emptiness where matter performs its play. The stage is alive. It bends, flexes, and responds to every actor upon it. The more massive the actor, the deeper the bow of the stage. The performance is mutual. Matter shapes the stage, and the stage shapes matter. This reciprocity defines all gravitational phenomena, from the falling of an apple to the swirling of galaxies. Yet, this fabric has limits. If enough mass is packed into a small enough space, the curvature grows without bound. The metric predicts that there exists a radius beyond which the geometry folds entirely in upon itself. That radius defines the event horizon. It is not merely a boundary in space, but a transition in the structure of time. Beyond it, time and space exchange roles. and the path forward leads only inward. To understand what it means for time to bend so far that it turns upon itself, we must look closely at the equations that describe motion near this limit. They tell us that as one approaches the horizon, every attempt to remain stationary requires infinite acceleration. Hovering there is impossible. The geometry itself demands motion inward. The closer one gets, the less the concept of rest retains meaning. Einstein once described this interplay between matter and geometry as the greatest and simplest of all ideas. That space and time are not the backdrop of existence, but part of it. Gravity, in his view, was the manifestation of reality's flexibility. The discovery that time can stretch, slow, or even halt depending on curvature is the direct consequence of that flexibility. Everywhere in the universe, from the surface of planets to the hearts of black holes, time follows the contours carved by energy. To trace those contours is to glimpse the machinery behind all motion. To stand near a massive object is to feel the weight of geometry itself pressing upon the seconds of one's life. And to cross the event horizon is to enter a region where the familiar order of time and space ceases to apply. In this way, gravity is not an external influence acting upon the world. It is the world's own shape evolving. When the equations are written, they do not speak of forces or fields, but of curvature, of metrics, of the way the universe measures itself. Within that geometry, time is not an independent flow, but a coordinate molded by the same hand that sculpts space. This understanding leads us to a profound realization. The event horizon is not simply a frontier of gravity, it is a frontier of meaning. Beyond it, our notions of distance and duration break down. What lies within can only be described in terms of what crosses it, never what remains behind. The fabric that bends also hides. To explore this hiding place, to see what the geometry conceals within its perfect curve, we must follow the path of light itself, the last messenger permitted to linger at the threshold of eternity. For light alone can trace the exact shape of the horizon, skimming its surface in the balance between escape and capture. If you were to send a beam of light grazing the surface of a black hole, that light would trace the most perfect expression of space-time's curvature ever found in nature. Each photon, massless and free, follows the geometry as faithfully as a leaf adrift upon a cosmic tide. The bending it experiences is not a distortion in its own motion, but a reflection of the shape through which it moves. At a certain distance, known as the photon sphere, light can circle the black hole endlessly, balanced on the knife's edge between falling inward and escaping outward. Here, the geometry itself defines the path, trapping light in a perpetual orbit around nothing but the curvature of reality. This region exists at 1.5 times the Schwarzschild radius. It is a place of exquisite instability. A single disturbance sends photons spiraling inward to the horizon, or outward into the universe once more. No other structure in physics demonstrates more clearly that space and time are living entities, capable of shaping the fate of light itself. When astronomers observe the dark silhouette of a black hole against the glowing swirl of infalling matter, what they see is not the object itself, but the shadow cast by this photon sphere, a ring sculpted by geometry. To grasp how space-time achieves this, we must imagine what the equations describe. Einstein's field equations form a set of interlocking relationships that govern how mass and energy curve the universe. When solved for a single spherical mass, they yield a picture of space-time where every radial direction is stretched and every temporal interval is slowed. The equations are written not to describe motion through space, but the very scaffolding upon which space and time rest. Near the horizon, the curvature becomes so severe that the meaning of motion changes. The direction one calls outward ceases to exist in the normal sense. The geometry folds such that every line of travel, every beam of light, every tick of a clock bends toward the singularity. Space itself no longer extends outward from the center. Instead, it funnels inward like a vortex, in which time itself has become the current. Imagine a traveler descending toward that boundary. Their ship's instruments record increasing gravitational acceleration. Each signal sent outward is stretched in frequency, each response from home delayed. The traveler experiences the fall as swift and smooth. They pass the horizon unaware, seeing only the stars above compressed into a thin ring of light as the sky narrows behind them. To them, time remains constant, unbroken. But to the distant observer, that traveler has slowed to near stillness, their final message frozen in an eternal whisper at the edge of the black hole. In this interplay between perception and geometry lies the profound unity of Einstein's vision. Time and space are not separate arenas in which events unfold. They are coordinates within a single four-dimensional structure, and that structure bends according to the matter within it. The curvature does not merely influence the passage of time, it defines it. The ticking of a clock is nothing more than the universe measuring its own geometry. When the equations of general relativity are written, they describe how the curvature tensor relates to the distribution of energy and pressure. What we call gravity emerges naturally from this relationship. The greater the mass, the steeper the curvature. The steeper the curvature, the slower the passage of time. In regions where energy density is low, space-time appears nearly flat and time flows uniformly. In regions where matter collapses into enormous compactness, space-time folds inward and time slows to a crawl. This perspective also transforms our understanding of motion. An object in free fall is not being pulled. It is moving straight through curved space-time. Its path, called a geodesic, represents the natural motion of any object, unaffected by external forces. When a planet orbits a star, it is following such a path, curving not because of a pull, but because space-time itself tells it to. Gravity, then, is not a force that causes acceleration. It is the geometry that defines what straight means in the first place. This realization is among the most subtle and powerful in science. It tells us that to understand the universe, one must understand geometry. The distances between stars, the motion of galaxies, even the flow of time in our own lives, all are expressions of how space-time measures itself. The metric is not a background, it is the essence. When we apply these principles to the cosmos as a whole, we find that the same equations governing black holes also govern the expansion of the universe. The curvature caused by mass and energy dictates not only local motion, but the grand evolution of space-time itself. Galaxies drift apart because the geometry between them stretches. Time and space are born together in that expansion, their relationship set by the balance of matter, radiation, and the mysterious dark energy that drives acceleration. In this cosmic dance, black holes serve as counterpoints, regions where the curvature folds inward instead of outward. They are the complements to cosmic expansion, the places where space-time caves in on itself. In both extremes, the fabric of reality reveals its flexibility. Whether expanding or collapsing, it follows the same law. Energy determines geometry, and geometry determines time. It is no wonder, then, that near the event horizon, the nature of time feels so alien. The geometry there is the most extreme manifestation of Einstein's equations. Each tick of a clock corresponds to a deeper descent into curvature, each pulse of light an echo slowed by the shape of the universe itself. From this arises the profound truth. Time is not universal, because curvature is not universal. Each point in space-time has its own rhythm, dictated by its own geometry. As we continue to explore this concept, we realize that the horizon's mystery lies not in the mass that creates it, but in the geometry that defines it. The equations tell us that the event horizon is where space-time's structure bends so completely that all future paths point inward. But they also whisper something deeper, that this boundary is not an edge in the traditional sense, but a surface of transformation, where our familiar notions of distance, duration, and cause lose their meaning. In this light, Gravity ceases to be a simple actor in the play of forces. It becomes the stage itself. Its script is written not in lines of attraction and repulsion, but in the curvature of existence. The same mathematics that governs the orbit of planets also determines the death of stars and the birth of time near horizons. To glimpse this in its purest form, one must follow space-time beyond the horizon, into the region where the normal rules of geometry no longer hold, and where time itself becomes another coordinate pointing inward. There, the very meaning of direction changes, and the idea of standing still becomes impossible. To move beyond metaphor, imagine that you could follow a particle as it fell freely toward a black hole. At first, it accelerates as any object would under gravity, gaining speed as it descends through the curved geometry. But the deeper it falls, the more its path through space-time tilts toward the future that lies inward. To the distant observer, the particle slows, its light stretching into red, fading into invisibility. Yet to the particle itself, there is no slowing, no hesitation. It continues naturally, tracing the straightest possible line through a space-time that has folded in upon itself. This strange inversion of experience reveals something essential. Inside the horizon, space and time trade identities. What was once a spatial direction, the inward path, becomes a temporal one, unavoidable and singular. Just as you cannot stop moving from one second to the next, no object inside the horizon can stop moving toward the singularity. The inward direction becomes as inevitable as tomorrow. The Schwarzschild metric encodes this directly. Its terms swap their signatures beyond the event horizon. The coordinate that once measured distance now measures duration. The geometry dictates this reversal not as a trick of perception, but as a mathematical necessity. The consequence is astonishing. Within a black hole, there are no stable positions, no fixed places in space. Everything falls, because falling is what time means there. In this sense, the singularity at the center is not a place but a moment, the final one on every possible timeline that enters the horizon. It is where the curvature of space-time becomes infinite, where the equations that describe the universe lose meaning. All paths end there, just as all moments in an ordinary life end in the future. The singularity is not a destination in space, but the inevitable conclusion of time within the horizon. For an outside observer, this conclusion is unreachable. They see only the endless slowing, the asymptotic freezing at the event horizon. No light returns, no information escapes. Yet from the inside, everything proceeds as normal until the very end. This contradiction lies at the heart of relativity's power. It allows multiple realities to coexist, each confined to its own geometry, each true within its own domain. The fabric that bends thus creates not just gravity, but the limits of what can be known. When space-time folds beyond a certain point, observation itself becomes impossible. The equations predict that any attempt to retrieve information from beyond the horizon fails, not because of technological limitation, but because the structure of causality forbids it. The horizon is the ultimate one-way surface, where all paths of light and time flow inward. This deep unity between geometry and destiny is what makes black holes the most profound expressions of Einstein's theory. They are not merely dense objects. They are solutions to equations, pure manifestations of curvature. The horizon is not built of matter. It is a surface defined entirely by geometry. What we see as darkness is the absence of paths that lead outward. To understand this in human terms, consider the experience of standing on Earth. We resist the pull of gravity, feeling weight because the ground pushes us upward, away from our natural free-fall path. If the ground were removed, we would fall freely, feeling weightless. Inside the horizon, there is no ground, no way to resist. The natural path is always inward, and no force can oppose it. In this way, a black hole is not simply a region where gravity is strong. It is a region where the concept of standing still ceases to exist. the bending of space-time becomes complete, transforming all possible motions into one inevitable journey toward the singularity. Space and time cease to be distinct directions. They merge into a single flow, uniting motion and existence in their final expression. Einstein's vision revealed that all of this follows from the simplest principle: space-time responds to energy. From that one statement arises every feature of gravity, from the gentle fall of rain to the crushing collapse of stars. The equations are indifferent to scale. The same geometry that curves the orbit of Earth around the Sun also shapes the death of light at the horizon of a black hole. As we trace these curves across the cosmos, we come to see the universe not as a collection of separate things, but as a single connected structure, a fabric whose every fold and ripple carries the story of its contents. In this view, time itself is one of those ripples. It is not an external clock, but a dimension molded by gravity, expanding and contracting with the universe's shape. Thus, the study of curvature is the study of time. To measure gravity is to measure how reality flows. Every massive object is a sculptor, shaping the geometry that defines the seconds around it. In the emptiness between stars, time stretches freely. Near their surfaces, it slows. Near the horizon, it nearly stops. The universe's rhythm is written in these gradients. We have now followed this geometry from the gentle slopes of Earth's gravity to the steep precipices near the horizon. Yet what happens beyond that precipice remains hidden, not by secrecy, but by the structure of space-time itself. To see inside, we must accept a new kind of viewpoint, one that falls freely, surrendering the outside world's sense of time. In the next chapter, we will cross that threshold. We will follow matter and light beyond the horizon, into a realm where the coordinates of time and space trade roles completely, and where every future leads to the same inevitable end. For there, within the fabric that bends, lies the most profound mystery of all, the place where time itself begins to die. There is a line in the universe that no traveler can cross and return from. It is not drawn by light or matter, but by geometry itself. It marks the point where escape becomes impossible, where the flow of time and the pull of gravity merge into one and the same thing. That line is the event horizon, the border between the visible universe and the unknowable interior of a black hole. To understand what happens at this horizon, imagine a beam of light fired outward from just above it. Far from the black hole, light races freely through space at its universal speed. But as it climbs from near the horizon, the curvature of space-time stretches its wavelength. Each photon loses energy, redshifted by the deep gravitational well. The closer it begins to the horizon, the longer its climb and the greater its loss, until at the very edge, the light no longer escapes at all. It lingers there, frozen, its energy stretched into infinity. From the viewpoint of a distant observer, this is what defines the event horizon, the surface where time itself seems to stop. Any process occurring there slows endlessly, never completing. A clock descending toward the horizon appears to freeze, its final tick never arriving. The falling object's image fades, dimming and reddening until it vanishes entirely. It is as if time itself, for that object, has been trapped, suspended in an eternal moment at the brink of reality. Yet from the falling traveler's own perspective, nothing so dramatic occurs. They experience no wall, no boundary, no sudden shift. The horizon is not a surface in space, but a feature of space-time geometry. The traveler passes it freely, without noticing, in the same way that one might cross an invisible line on a map. Their watch continues to tick, their heart continues to beat. They see the universe above them compressed into a narrow cone of light, the stars drawn together by gravity's lensing, but no catastrophe announces their crossing. This is one of the strangest dualities in physics. To the outside world, time stops at the horizon, but to the falling observer, it flows unbroken. Both experiences are real, yet irreconcilable. They coexist because space-time allows multiple truths, each defined by the observer's own path through geometry. The horizon divides these realities as perfectly as it divides space. It can be tempting to think of this frozen appearance as illusion, but it is no trick of light or perspective. It is a direct consequence of how space-time warps near immense mass. Time dilation becomes infinite at the horizon. To the outside universe, every process at that boundary unfolds infinitely slowly. The traveler seems suspended forever in their final instant. From within, however, the equations reveal that the traveler crosses the horizon after a finite proper time, measured on their own clock. The distinction between never and soon depends entirely on the observer. Einstein's geometry describes this boundary with exquisite precision. At the Schwarzschild radius, the curvature of space-time bends so deeply that the light cones, the structures that define all possible paths through time, tip inward completely. No future path leads outward anymore. Everything, including light, moves toward the singularity. This is not because light slows down, but because space-time itself carries all motion inward. The horizon is therefore not a wall, but a flow, a surface where time and space tilt into each other until escape becomes meaningless. This geometry also defines the horizon as a null surface, a region where the separation between one moment and the next, for an outside observer, becomes infinite. If you were to send a sequence of signals from a falling spacecraft, each spaced evenly by the traveler's own clock, the distant observer would receive them ever more slowly. The intervals between signals stretch, their frequencies decline, and eventually they stop arriving altogether. The last transmission lingers endlessly at the edge of the black hole's image, fading into darkness. The horizon's very nature defies the everyday meaning of boundary. In ordinary experience, a boundary separates two regions of space. Here, it separates two regions of space-time itself, two different realities of causality. Outside the horizon, one can still move freely, choosing directions in both space and time. Inside, the geometry dictates a single future. Inward, all paths lead toward the singularity. The horizon is therefore not a barrier that resists crossing, but a threshold that marks the end of freedom. To stand outside the horizon and watch matter fall in is to witness the slow death of time. A star collapsing into its own gravity appears to pause, its outer layers frozen just above the Schwarzschild radius. But this is only appearance. The star continues to collapse in its own frame, forming a black hole in finite time. The illusion of stillness is a product of our distance and of the infinite dilation imposed by curvature. From the outside, the star never finishes its fall. From the inside, the process completes naturally. This duality creates a profound tension in how we think about reality. Which version is true? The one where the fall ends, or the one where it never does? Einstein's equations say both are. The concept of now loses meaning across the horizon because simultaneity itself dissolves in curved space-time. There is no shared clock that unites the inside and the outside. Each region exists in its own temporal domain, connected only through light that never quite escapes. To visualize this, imagine an observer hovering just above the horizon, holding steady with enormous thrust. For them, every second feels normal. But to the distant universe, their clock ticks ever more slowly. To hover closer still would require infinite energy. The geometry forbids stasis at the horizon because it would mean resisting the flow of time itself. The only path permitted, there is free fall. The universe does not allow standing still on the edge of eternity. This limit defines more than just black holes. It defines the structure of time itself. The horizon shows that time and gravity are inseparable. Where gravity is strong, time slows. Where gravity is infinite, time halts. The event horizon is the place where that relationship reaches perfection. It is the physical embodiment of the principle that space and time are one fabric, and that bending, one bends the other. Even light, the universe's fastest traveler, is not immune. At the horizon, its outward motion matches the inward flow of space-time exactly. The light moves outward at the speed of light, yet it never gains ground, forever trapped in the same place in geometry. This balance defines the surface of no return. The horizon is where motion and stillness become the same. In this perfect symmetry lies the ultimate consequence of relativity. Gravity can slow time, and curvature can redirect motion. But at the event horizon, the two effects merge completely. Time becomes geometry, geometry becomes destiny, and every object, every photon, every shred of information is carried inward by the structure of space-time itself. To stand before a black hole, even in imagination, is to stand at the boundary between being and nothingness. If you could hover above that abyss and watch another traveler fall toward it, you would see a sight unlike anything else in nature. The closer they approach the horizon, the slower they appear to move. Their motions stretch into eternity, their final gestures fading into the dark. Light from their ship reddens, its wavelength stretched by gravity's pull until it disappears entirely. Their image freezes, suspended forever at the threshold. From your distant viewpoint, time itself has stopped for them. Every moment you see takes longer to unfold. Every clock aboard their vessel ticks more slowly. As they near the event horizon, your instruments record a halt. It seems as though your friend has been captured not only in space, but in time. Yet you know, through the equations of relativity, that their own experience is nothing like this. To them, seconds pass normally. The engines hum. The stars above appear warped, but still visible. The crossing happens silently, without warning, and within moments they are beyond your reach, carried into a region from which no light can return. This strange division of perspectives is not a flaw in physics. It is the essence of space-time itself. Both viewpoints are correct. For the external observer, the traveler never reaches the horizon. For the traveler, they cross it and continue inward. The contradiction is not paradox, but consequence, born from the fact that time is not absolute. Each observer carries their own space-time, their own rhythm of events. The geometry ensures that neither can see the other's experience beyond the horizon. If we could watch a collapsing star at the end of its life, we would see this dual reality unfold in slow motion. As its core compresses under its own weight, the outer layers fall inward, emitting bursts of light. These flashes grow fainter and redder with each passing moment. To us, the collapse seems to approach a halt, as though the star has become a dim, motionless sphere. In truth, the collapse continues unseen. The matter crosses the horizon and vanishes from the universe's visible ledger. The black hole forms completely, but from our perspective, the final stage remains forever in progress. The event horizon thus becomes the ultimate one-way gate. Nothing that crosses it can return, not because of destruction, but because the geometry forbids any path outward. Inside, all trajectories curve inward as surely as time itself moves forward. Outside, light can still climb away, though slowed by the gravitational field. At the horizon, these two domains meet perfectly, forming the surface where time dilation becomes infinite. This phenomenon, known as gravitational redshift, is one of the most direct consequences of the curvature of space-time. As light escapes a gravitational field, its energy decreases, stretching its wavelength. Near a black hole, this effect grows so extreme that light from the horizon is stretched beyond all detection. No telescope can see it. The photons that leave its edge are endlessly delayed, their frequencies approaching zero. What remains is darkness, not because nothing is there, but because all that remains is time itself, stretched into stillness. To describe this rigorously, physicists use the language of null surfaces. The event horizon is one such surface, defined not by material composition, but by the paths light can take. Every photon emitted at the horizon travels along that very surface, neither escaping outward nor falling inward. It rides the boundary between both fates. This is why the horizon can be thought of as the skin of a black hole, a surface of frozen light. But the horizon is also more than geometry. It is a boundary in meaning. Inside it, all concepts we use to describe space, above, below, near, far, lose coherence. The inward direction becomes the only future. To describe the inside of a black hole, one must invert intuition entirely. There is no way to remain still, no way to wait. Motion toward the singularity is as unavoidable as the ticking of a clock. Time itself has become direction. Outside the horizon, by contrast, time and space retain their familiar relationship. You can move through space while time flows steadily onward. Yet even there, near the boundary, the influence of curvature can be felt. Clocks close to the horizon tick slower than those farther away. Two observers exchanging signals find their frequencies mismatched, their mutual perception distorted. The nearer one descends, the greater the lag, until communication itself stretches into infinity. This relativity of time is not confined to black holes, it exists everywhere. Gravity exists, though faintly. On Earth, it causes clocks at mountain peaks to run a fraction of a second faster each year than those at sea level. The satellites orbiting overhead must account for this difference to keep our navigation systems accurate. These small corrections are whispers of the same geometry that becomes absolute at the horizon. The universe reveals its laws softly in daily life, and with cosmic finality at the edge of a black hole. Einstein's equations describe both extremes with the same grace. They tell us that wherever matter and energy reside, space-time bends, and wherever space-time bends, time itself adjusts to that curvature. There is no separate clock independent of gravity. Every clock, every heartbeat, every atomic oscillation measures the geometry in which it exists. Near a black hole, that geometry stretches the seconds into eternity. To imagine hovering at the horizon is to imagine confronting infinity. The energy required to resist the inward flow of space-time would be limitless. Any physical object attempting to remain there would be torn apart, not by tidal forces alone, but by the impossibility of standing still in a region where time itself flows inward. Free fall is the only option, because the geometry allows nothing else. In that surrender lies the true nature of the horizon. It is not a wall to be broken or a surface to be touched. It is a transition, a redefinition of the word possible. What happens inside is hidden forever from the outside, not by choice, but by the structure of causality itself. The universe draws a veil, not out of secrecy, but out of necessity. The horizon of no return is therefore not merely a place in space. It is an event in the structure of time, a point where the distinction between then and now becomes infinite. From the outside, all motion stops. From the inside, motion continues unimpeded. The two realities never meet again. The horizon is both a border and a mirror, reflecting the limits of what can be seen and known. To understand what truly defines the horizon of no return, we must return to first principles. The event horizon is not a material surface, not a membrane hovering in space, but the precise set of points where light itself becomes trapped. It is geometry distilled to its most absolute form. Every world line, every possible path through space-time that touches that surface flows inward thereafter. The horizon's shape is determined only by the mass, charge, and spin of the black hole, and its position marks the exact place where escape ceases to be meaningful. In mathematical terms, it is the surface where the escape velocity equals the speed of light. But this phrase hides a deeper reality. In curved space-time, the concept of velocity itself loses its usual definition. The horizon is not a limit of speed, but a limit of causality. Beyond it, every direction in space points toward the singularity, just as every second in time points toward tomorrow. No force, no photon, no signal can move against that inward tide. The geometry itself has rewritten the rules of possibility. When you fall toward the horizon, you are not pulled in the way a magnet pulls iron. You are simply moving naturally through space-time, following the straightest possible line that the geometry allows. Gravity does not act on you, it defines the path you take. The difference between inside and outside the horizon is therefore not about what happens to you, but about what paths exist at all. Inside, all roads lead to the singularity. Outside, some still lead away. To the external universe, the horizon appears as a perfect absorber. Every photon that ventures near it either bends back toward infinity or vanishes forever. The boundary itself emits nothing, reflects nothing, reveals nothing. It is a surface of absolute silence. The light from infalling matter never truly crosses it in the view of the distant observer. Instead, it fades, stretched infinitely thin, its information painted upon the surface of the horizon like a ghostly imprint. This picture gives rise to one of the most haunting ideas in modern physics, that everything falling into a black hole leaves its record upon the horizon itself. The external universe sees not the disappearance of matter, but the freezing of its final moment. The horizon becomes a cosmic archive, a two-dimensional record of all that has entered, preserved in slow motion for eternity. Yet even this is incomplete. The traveler who crosses the horizon experiences none of this freezing, none of this delay. For them, the journey continues unbroken. The geometry inside the horizon is not the geometry of the outside world. There, space and time have exchanged their roles. Moving inward is no longer an option, it is a necessity. The singularity lies ahead, not as a place, but as the next instant of time. The contrast between these two realities reveals something profound about the nature of the universe. Time is not a single, universal flow shared by all observers. It is a local experience, sculpted by gravity. The horizon is where this relativity becomes infinite, where two perspectives diverge so completely that they can never be reconciled. To the outside universe, time stops at the horizon. To the traveler, time continues without pause. Both are true, each within its own geometry. For the distant observer, this leads to an eerie consequence. The universe appears to accumulate frozen matter on the surface of the black hole, each piece slowing endlessly as it nears the horizon. The black hole seems to grow not by swallowing matter, but by layering these frozen images upon its edge. Yet for the matter itself, that surface does not exist. It passes through and disappears from the visible universe. The event horizon is therefore both the most real and the most elusive structure in existence, a boundary that exists only because of the way space-time divides viewpoints. This duality forces us to question the meaning of reality. What does it mean for something to exist if it can never again be observed, never again communicate with the outside? In the geometry of a black hole, existence itself becomes relative. The horizon marks the point beyond which events cease to have effects on the rest of the universe. In that sense, the inside is cut from the cosmic narrative. For those outside, it is as though it has fallen from time. Einstein's theory predicted these consequences, but it did not diminish their mystery. To him, the event horizon was not an object, but a mathematical boundary, a place where our coordinates lose meaning. Later, physicists would explore this further, discovering that horizons exist not only around black holes, but wherever space-time accelerates strongly enough to create regions that are causally isolated. The horizon is a general feature of relativity, a universal symbol of limits. Every horizon, whether cosmic or personal, marks a region of unreachability, a domain beyond which no message can return. The black hole's event horizon is simply the most perfect of these. It demonstrates that the universe allows regions sealed off from influence, where time flows differently, and where causality itself folds inward. The horizon of no return is thus both boundary and mirror. It reflects our ignorance, showing us where observation ends, but it also reflects our own motion through time. In a sense, each of us carries our own horizon, the limit of what we can know and what lies forever beyond our light. The black hole merely makes this truth visible. At this threshold, the universe reveals the fragility of its own structure. Time and space, which seem so separate and stable in daily life, are revealed to be intertwined and malleable. The horizon is not a cosmic anomaly. It is a statement about how reality works. When gravity grows strong enough, it bends not just paths and orbits, but the very concept of the present. And yet even here, in the most extreme curvature imaginable, the equations still hold. They predict not chaos, but order, a smooth continuation of space-time through the horizon. For the falling observer, the crossing is calm, silent, unremarkable. Only deeper within, as the singularity approaches, does the geometry reach its breaking point. There, all paths end, and time itself ceases to have meaning. The horizon, then, is not merely the edge of a black hole. It is the edge of understanding. Beyond it, our theories falter, and our words lose definition. To go further, we must follow the traveler inside, into a domain where time no longer behaves as we know it, and where the universe reveals its most secret symmetry, the slow death of time itself. Imagine a clock falling toward a black hole. From afar, you watch its ticking slow until each second takes longer than the last. Its face fades, its hands hesitate, and then they seem to stop. The final moment stretches endlessly, as though time itself were being pulled apart by the same gravity that draws the clock inward. This is not a trick of vision or a failure of light. It is the nature of space-time itself. Near the horizon, time's rhythm falters, stretched thin by gravity until it can no longer continue. Einstein taught us that time is not absolute. It bends and flexes with the curvature of space-time. On Earth, this effect is small, so small that we never notice it. A clock in orbit ticks slightly faster than one on the ground because it feels less gravity. A mountaintop runs ahead of a valley by billionths of a second each day. But near a black hole, those small differences become vast. The same equations that keep satellites synchronized predict that, close to the event horizon, time for the falling clock nearly stops. To a distant observer, the clock's descent becomes an endless approach. Each flash of light it sends takes longer to reach you. Each signal is weaker and redder than the one before. Soon the clock's light fades beyond detection, yet mathematically it never crosses the horizon. The last photon it emits will take forever to arrive. The clock is gone, and yet, from your vantage point, it remains, forever frozen on the edge. This strange spectacle is what we call gravitational time dilation, carried to its ultimate extreme. It is not that time has stopped for the falling object, but that the connection between its time and yours has broken. The geometry of space-time has stretched the bridge between you until it reaches infinity. Communication ceases, not because signals fail, but because they can never catch up. If we reverse the view and imagine ourselves falling, the experience changes completely. From our perspective, the distant universe seems to accelerate. The light from the stars ahead blue shifts, their wavelengths compressed, their motion rushing forward as though the cosmos were aging in fast motion. We cross the horizon in finite time, unaware that the rest of the universe will never see us do so. For us, time continues normally. For them, it ends. This dissonance between the two perspectives is one of the most profound aspects of relativity. It shows that time is not universal, it belongs to each observer. The gravitational field determines how quickly or slowly it flows. Where gravity is stronger, time slows. Where it is infinite, time halts. The event horizon is simply the place where this relationship reaches its limit. Now imagine a star collapsing under its own gravity. Its outer layers fall inward, compressing the core. As the collapse deepens, gravity grows stronger, the curvature sharper. To an external observer, the star's surface slows its fall, glowing redder and fainter until it seems to freeze. But in its own frame, the star continues collapsing smoothly, crossing the horizon and falling toward the singularity in seconds. The universe outside watches it die forever. The star experiences its death in an instant. Both are true, bound by geometry and divided by perception. From the outside, it appears as though time itself has been trapped at the horizon. Nothing new seems to happen there. No motion, no change, only a silent, eternal stillness. But that stillness is an illusion born of relativity. Inside, events unfold as always. Time is not destroyed. It is merely severed from the outside universe. The horizon acts like a mirror that shows the final image of everything that crosses it, but never reveals what happens beyond. To visualize this, think of the light emitted by an object as it falls. Each wave of light climbs out of a deeper gravitational well. The deeper it begins, the more stretched it becomes. At the horizon, the waves are infinitely long, so long that they carry no energy. This is why the object's light fades to black. It is not gone, but its energy has been diluted across infinite time. The object's image remains suspended at the horizon, eternally redshifted, eternally unreachable. The physics behind this is captured in the same equations that describe all of general relativity. The rate of time flow for an observer at a distance depends on the gravitational potential they inhabit. As this potential deepens, the passage of proper time, time measured by a local clock, slows relative to distant clocks. At the horizon, this slowdown becomes infinite. The geometry ensures that no event inside can influence the outside ever again. In the gravitational collapse of a star, this process plays out on cosmic scales. The outer layers seem to hang frozen, but in reality, the star's mass has already passed beyond the horizon. From the viewpoint of the external universe, the black hole's boundary grows as more matter falls in. From within, everything rushes onward toward the singularity, a place in space-time where curvature becomes infinite and the known laws of physics fail. To watch such a collapse is to witness the slow death of time. The star fades, not because its light ends, but because its time has slipped beyond reach. The horizon becomes the grave of moments, the place where the ticking of the universe itself ceases to continue. From our side, we see its past, but never its future. From within, the future continues until even the concept of time dissolves. It is a haunting symmetry. For the external observer, the horizon is eternal, unchanging, frozen, perfect. For the infalling matter, it is fleeting, passed without notice. In both views, the laws of physics hold absolutely. What changes is the meaning of now. The notion that time can stop challenges our deepest intuitions. We think of time as universal, constant, flowing independently of where we are. Yet the black hole teaches otherwise. Time is a property of space-time, not something outside it. When space-time curves enough, time's flow bends too. In the strongest curvature, that flow ceases altogether. And still, this death of time is not destruction, it is transformation. Inside the horizon, time continues, but it leads inexorably toward the singularity. Outside, time halts for anything that has crossed. The black hole divides existence into two realms, one where moments still unfold, and one where they are forever complete. The slow death of time is therefore not an ending, but a boundary. It marks the limit of connection between observers, the ultimate horizon of causality. Beyond it, time flows in directions we cannot share. Within it, the universe continues, unseen. The horizon does not end reality, it separates realities. And so, as we gaze upon a black hole, we are witnessing a cosmic paradox made real. We see the living face of relativity itself. time stretching into infinity, light slowing into stillness, and the universe folding its own history into silence. The horizon is not merely a region of gravity, it is the surface where time, as we understand it, loses meaning. In the chapters ahead, we will follow what happens to time beyond that surface. For inside the horizon, the rules change once more. Space and time trade roles completely. The future becomes a direction in space, and the inward fall becomes as inevitable as the passage of moments in our own world. The slow death of time at the horizon gives way to something even stranger, the redefinition of what time is. If you could fall toward a black hole and record what you saw, your footage would be among the strangest films in the universe. As you drift closer, the stars above would begin to distort, their light bending into a luminous halo encircling the blackness ahead. The deeper you fall, the more your view compresses into that ring of fire. Behind you, the rest of the universe stretches, its light blue shifting as your descent accelerates. You would feel no pull, no wrenching force, just the smooth sensation of free fall. Gravity would no longer feel like gravity at all. It would feel like the geometry of time itself, guiding you forward. The clock on your wrist ticks normally, but when you compare it to the one you left behind, the difference becomes immeasurable. Hours for you might be years, centuries, or millennia for the outside world. In the extreme gravity near the horizon, this effect grows beyond comparison. The outside universe rushes forward at incredible speed. Stars live and die in the blink of your eye. Galaxies rotate through their lifetimes before you cross the event horizon. For you, the descent is brief. For the cosmos, it lasts forever. This is not imagination, but mathematics. The closer you are to the Schwarzschild radius, the stronger the warping of space-time. The relation between proper time, your time, and coordinate time, the universe's time, becomes infinite. To an outside observer, you have slowed to near stillness. To yourself, nothing has changed. The slow death of time is not a process you experience. It is something that happens to those who watch you from afar. Now, picture a star collapsing into a black hole. The outer layers glow with heat and fury as they fall inward. Light radiates outward, carrying the final message of the dying star. But gravity stretches those messages endlessly. The last moments of the star's life play in eternal slow motion, its light stretched to invisibility. The black hole that remains seems to wear the star's final moment as its surface, frozen in time. Yet within, the star has already passed into oblivion. This strange duality gives the horizon its power. It is the ultimate mirror of time, showing two truths that cannot coexist, and yet both are real. The observer outside sees eternity. The traveler inside feels only moments. One sees the death of time, the other lives through its continuation. Einstein's equations do not choose between them. The geometry simply contains both. What happens to the light emitted just before the horizon is crossed is perhaps the most haunting part of this story. Each photon climbs through a deeper gravitational well, losing energy, lengthening in wavelength. Its frequency slows until it becomes radio waves, then whispers of microwave radiation, then nothing at all. The light never vanishes, it just fades beyond all possible detection. Somewhere, at the edge of the black hole's image, those photons still linger, frozen in infinite redshift. From the outside, this effect means that we never truly see anything fall into a black hole. We only see it approach the horizon, slowing and dimming. The horizon acts like a cosmic time capsule, preserving the final images of all that has fallen within. But the capsule never opens, because from our perspective, its moments never finish unfolding. Inside the horizon, time flows differently. The coordinates we use to describe space and time outside no longer apply. The inward direction becomes a direction in time itself. You cannot hover or turn back. Every possible motion carries you closer to the singularity. The pull you feel is not a force, but a consequence of geometry. You are not being dragged, you are being carried by the shape of space-time. Physicists often describe this change as a swapping of roles between space and time. Outside the horizon, you can move in space while time moves forward. Inside, what was once space becomes your future. To remain at a fixed distance from the singularity would be like trying to stay at a fixed moment in time. It cannot be done. The black hole does not pull you in. It simply defines the future as inward. The singularity at the center is the place where all possible futures converge. Every trajectory, every beam of light, every path through space-time ends there. The equations that describe this region break down, curvature becomes infinite, and the known laws of physics cease to hold. The singularity is not a point in space, but an ending in time, a place that cannot be reached without the destruction of meaning itself. From our distant view, this end never arrives. We see only the approach, the slowing, the fading. The black hole thus stands as a monument to relativity, a place where perception itself becomes relative and where the flow of time depends entirely on one's path through space-time. This concept, the separation between local and global time, is not limited to black holes. It is built into the structure of the universe itself. Every region of space-time has its own rhythm, its own measure of the flow of time. The black hole is simply the extreme case, where that rhythm becomes infinitely different from the universe around it. To grasp this deeply is to see that gravity does not just pull, it sculpts the flow of reality. When we speak of time slowing near massive bodies, we are really saying that gravity changes the rate at which existence unfolds. Each second near a black hole contains infinitely more geometry than a second far away. The slow death of time, then, is not just a phenomenon, it is a revelation. It tells us that time is not an independent backdrop, but a property of the universe's shape. When the shape bends enough, the ticking of clocks and the motion of light are bound by it. The horizon is the place where this bond reaches perfection, where time becomes geometry and geometry becomes fate. The black hole is often imagined as destruction, but in truth, it is transformation. It converts the energy of motion, the flow of time, the very fabric of space-time, into a single smooth continuation that no longer connects to the outside. For everything beyond the horizon, time's story ends. For everything within, it continues toward the singularity, where that story loses its final meaning. If one could speak of what it feels like to fall forever, perhaps this would be the description. No pain, no force, only the relentless deepening of silence. The universe above fades into darkness, stretched across your vision into a narrow ring. The sound of time itself recedes, leaving only the geometry of inevitability. You are not destroyed yet. You are merely becoming part of the black hole's future. And from the outside, that future is already over. The horizon holds your image frozen in the eternal stillness of time that no longer flows. You have become both gone and present, both finished and unending. The black hole's event horizon is the perfect stage on which the universe performs its slowest act, the death of time. Imagine watching an object drift toward that boundary. You would see its light delay, its color stretch to red, its motions drawn out until they freeze entirely. This is not a flaw in perception, but a truth written into the structure of space-time. At the horizon, the difference between before and after vanishes for the outside observer. The black hole does not simply swallow matter, it consumes the meaning of time itself. To those who fall, however, there is no pause, no hesitation. Their fall continues as naturally as ours, through seconds and minutes. Inside the horizon, time retains its rhythm, though its direction is now inward. The geometry demands that every future lies closer to the singularity. To them, the crossing is uneventful. To us, it is forever incomplete. The black hole thus divides existence into two truths that will never meet again. This separation is not unique to black holes. It exists wherever gravity is strong enough to distort time. On neutron stars, a few kilometers can stretch seconds into hours. On Earth, a difference of altitude can stretch nanoseconds. Everywhere, gravity sculpts time's flow, from the faintest whisper to the eternal stillness at the horizon. The black hole is simply the final verse of that cosmic symphony. To think of time dying might seem poetic, but it is literal. As the gravitational potential deepens, the intervals between events, as measured from afar, grow without bound. The external universe witnesses an infinite delay in the unfolding of any process near the horizon. It is not that time ceases within the black hole. It is that connection to the outer universe has been severed. The thread that once linked moments across space-time is cut, leaving the inside and outside to evolve separately. What remains on the horizon is the ghost of that connection. The surface acts like a one-way mirror, reflecting the last visible moments of all that has crossed. To an observer far away, this ghost is the black hole's face, a perfectly still sphere from which nothing ever changes. Yet every atom of that image corresponds to matter long vanished within. The horizon is not a static surface, but a moving front in space-time, marking the edge between two domains of reality. Consider the collapse of a massive star. As it implodes, the outer layers fall inward, emitting light. That light escapes, but with greater difficulty as the collapse continues. To an outside observer, the flashes slow until they blur into one final dim glow. The horizon forms when the collapsing material reaches the critical radius. Beyond that instant, all remaining matter continues its descent unseen. The outside universe sees only the star's frozen face, a monument to the final second of its visible life. The notion that a black hole could be seen as a frozen image rather than an object of motion reshapes our idea of what exists. What we call the black hole's surface is not a physical layer of matter, but the last visible frame of everything that has fallen in. It is a recording etched in the geometry of space-time. The black hole's growth, as seen from afar, is the slow accumulation of these recorded moments. Its true interior remains hidden, its evolution invisible. Inside, time continues until the singularity. The equations tell us that curvature increases without limit as one approaches that point. Every path, every clock, every possibility terminates there. It is the ultimate future, the destination of all timelines within the horizon. Nothing can survive it, not because of heat or pressure in the familiar sense, but because geometry itself ends. There is no where or when beyond that point. It is the border where space-time ceases to exist, and yet the outside world never sees this end. From our vantage, the infalling matter never arrives. The singularity exists in theory, in mathematics, but in observation, it is always hidden by the infinite time dilation of the horizon. The death of time is therefore never witnessed. It is implied, predicted, but forever beyond reach. The universe hides its most profound transformation behind the veil of infinity. The slow death of time has consequences beyond black holes. It teaches that time is not a uniform current flowing through all existence, but a local phenomenon shaped by gravity. The stronger the gravity, the slower the current. Near a black hole, the current stops altogether, forming a still pool where all histories end. This same principle applies everywhere, from the subtle time differences in your body's own height to the cosmic expansion that stretches the universe itself. Time is elastic, and gravity is the hand that stretches it. In a way, we all live within gradients of time. The seconds on your wrist differ slightly from those in your head, from those high above Earth, from those in distant galaxies. The universe is a network of clocks, each keeping its own rhythm, each marking its own passage. Gravity unites them and separates them simultaneously. The black hole is simply the most extreme clock, a region where, for the outside world, the second hand never moves. To speak of time dying may sound final, but it is not the end of motion or change. Inside the horizon, time continues. Only its relation to the universe outside has ended. The slow death is not annihilation, but isolation. The black hole severs regions of space-time from the rest, creating domains where cause and effect can no longer connect with the external cosmos. The flow continues inward, but its story is no longer shared. At the edge of the horizon, therefore, we encounter not emptiness, but the ultimate boundary of understanding. It is the place where relativity itself becomes absolute, where time for one observer ceases while it continues for another. It is the demonstration that the universe is not bound by our human intuitions of before and after, here and there. Time's death is not tragedy, it is revelation. To watch the slow death of time is to glimpse the architecture of existence. It is to see that reality is written in geometry, that motion and stillness are two faces of the same law, and that what we call time is nothing more than the unfolding of space-time's curve. The horizon does not destroy, it defines. It marks the threshold between what can be known and what forever recedes into silence. And so, the clock falls, its ticking stretched into infinity, its final moment preserved at the horizon's edge. From one side, time ends. From the other, it continues until meaning itself dissolves. The slow death of time is the universe showing us that eternity is not endless duration, but the stillness at the edge of all possible moments. Once the horizon is crossed, the universe changes its rules. What was once a boundary in space becomes a one-way passage in time. The event horizon is not a wall or a surface in any ordinary sense. It is a transformation of geometry. To cross it is to enter a region where the fabric of space-time itself has turned inside out, where the coordinates that once defined distance and duration exchange their meanings. The inward direction becomes time's arrow, and all paths lead inevitably to the singularity. Imagine the moment of crossing. To an outside observer, you are still frozen at the edge, your image fading in infinite redshift. But from your own perspective, the transition is seamless. There is no flash, no barrier, no sign that you have passed a limit beyond which no light can escape. You are simply falling, as you always have, carried along by the geometry of space-time. Yet something profound has changed. The direction you once thought of as space, the line pointing inward, has become your future. No matter how you steer, no matter what engines you fire, you cannot choose another direction. The singularity awaits, not as a destination you can reach in space, but as the next instant in your unfolding time. Outside the horizon, space and time behave as we expect. You can remain still, and seconds will pass. You can move through space in any direction you choose. But inside, these freedoms collapse. You cannot hover or pause, because inside the horizon, standing still would mean not moving forward in time. To exist there is to fall. The curvature of space-time dictates that the inward flow is as inevitable as the passage of seconds in our world. No physical law can resist it. This reversal of roles between space and time is one of the strangest consequences of general relativity. It is not mere metaphor, it is built into the mathematics of the Schwarzschild metric itself. The term that once described spatial distance becomes the measure of time. The coordinate that once marked your progress through time becomes a spatial direction. The geometry demands this exchange. Beyond the horizon, what we call inside and outside lose their usual meaning. Everything moves inward, because inward has become the future. From within, the horizon itself vanishes. You cannot look back and see it, because light cannot travel outward. The sky above, if such a word can still be used, narrows into a shrinking cone. The light from the universe you left behind is trapped, compressed into a thin halo of brilliance that encircles the direction of your fall. Ahead lies nothing visible, for the singularity emits no light and no signal can precede you toward it. All directions now lead inward. Every clock, every beam of light, every particle shares your fate. As you fall deeper, the curvature grows stronger, space stretches, and time compresses. The tidal forces begin to reveal their presence. Near the singularity, they become extreme. Your head and feet, separated by even a few meters, experience different gravitational pulls. The difference grows until it surpasses the strength of any material bond. This is sometimes called spaghettification, the stretching of matter into thin strands as it approaches the singularity. Yet this gruesome word hides a subtle truth. It is not a force tearing you apart, but the geometry of space-time itself diverging. Different parts of you are simply following different geodesics, different natural paths through a curvature that has grown infinitely steep. To imagine the singularity is to confront the limits of physics. It is the point where space-time curvature becomes infinite, where the known equations lose meaning. Inside the horizon, every future leads there, and yet we cannot describe what happens at that moment. The singularity is not a place within the universe. It is the end of the universe for that particular timeline. The geometry itself terminates. From a mathematical perspective, this singularity is the inevitable conclusion of Einstein's equations when mass collapses without limit. But those same equations also tell us that nothing inside the horizon can prevent that collapse. The structure of space-time ensures that all paths, all light cones, all futures converge. The singularity is the final punctuation in the story of every object that crosses the horizon. And yet, for the traveler, the experience of falling remains smooth until the very end. There is no warning of the singularity's approach. The stretching of time and space continues to intensify, but no local measurement reveals the cosmic catastrophe that awaits. The fall lasts a finite amount of proper time, a few seconds for a stellar mass black hole, or hours for a supermassive one. The universe outside ages immeasurably during that descent, but for the traveler, the end comes swiftly and silently. Within the horizon, the concepts of here and there dissolve. Space becomes a flow, a direction that cannot be reversed. Even if you were to shine a light directly outward, its path would bend inexorably inward, toward the singularity. The future has only one direction, and all things share it. There is no escape, no delay, no rest. Motion and time have merged completely. If we could see the geometry of the interior from an outside perspective, something no one can truly do, it would resemble a funnel without a bottom. The event horizon would be its rim, and the singularity its narrow end, infinitely deep. But this is not a structure in space, it is a structure in space-time. The fall inward is not a descent through distance, but a progression through time. Every instant brings you closer to the singularity, not because of motion through space, but because the geometry defines that inward flow as the passage of moments themselves. This is why physicists say that the singularity lies not ahead, but in the future. To ask what lies beyond it is meaningless, just as it would be meaningless to ask what lies beyond tomorrow. The singularity is the ultimate future for all that crosses the horizon, the end of time for that particular world line. What happens there, whether matter is crushed into infinite density or transformed by yet unknown quantum effects, is a question our current physics cannot answer. Einstein's theory predicts the singularity, but it also warns us that its presence signals the breakdown of that theory. The curvature becomes so great that quantum effects can no longer be ignored. At such scales, space-time itself may fluctuate, its geometry no longer continuous but granular, perhaps woven of discrete elements beyond our comprehension. The singularity, then, may not be a point of infinite density, but a region where our classical understanding of reality fails. the black hole's interior might be the birthplace of new physics, a realm where time and space are redefined at the most fundamental level. For now, the singularity remains beyond observation. No signal escapes from within the horizon to reveal its nature. The black hole hides its secrets perfectly. From the outside, it appears as a dark sphere of nothingness, its surface smooth, featureless, and silent. All the complexity of what has fallen in, stars, planets, light, information, is erased from view. The horizon holds no texture, no trace of what lies beyond. Yet in the equations, that hidden region continues to evolve, governed by the same geometric laws that shape the rest of the universe. The notion that space and time can trade roles, that falling inward becomes equivalent to moving forward, challenges every instinct we have about reality. But this is not speculation, it is geometry. Einstein's equations demand it, and the evidence from every observation of gravity supports it. The universe is not built upon a static stage. It is a dynamic fabric, bending, twisting, and in the case of black holes, folding upon itself. Inside the horizon, causality remains intact, but redirected. Events still follow one another in order, but that order leads only toward the singularity. Every clock agrees on the direction of time, even if the concept of where has lost meaning. The laws of physics continue to operate, but they do so in a domain from which no information can return. The black hole thus becomes not a hole in space, but a region of space-time isolated from the rest of the universe, a self-contained chapter in the cosmic story, forever closed to outside readers. And yet, the existence of that interior changes the universe beyond. The black hole's mass curves space-time around it, shaping the orbits of stars and bending the paths of light. Its presence sculpts galaxies, anchors quasars, and influences the motion of entire systems. Though nothing escapes from within, its gravity reaches outward, the echo of all that has fallen inside. To stand on the outside and contemplate the inside is to realize that the black hole is not an object, but a process. It is the transformation of space and time under the rule of geometry. The horizon marks the limit of what can be seen. Beyond it, time becomes direction, and direction becomes destiny. The traveler who crosses the horizon does not fall into an abyss, but moves forward in a new kind of time, a time that ends at the singularity. The universe above will never see their journey completed, but for them, it will unfold naturally. The horizon divides not just space, but the meaning of existence itself. In the chapters to come, we will examine what happens to light that hovers near this boundary, to information that seems to vanish beyond it, and to the deep question of whether the horizon itself might hold the key to preserving the universe's hidden memory. For now, as we leave the interior of the black hole in imagination, we carry this realization with us. Inside the horizon, time does not end because of destruction. It ends because geometry leaves it nowhere else to go. Around a black hole, even light cannot move freely. It dances along paths curved by gravity, caught between escape and surrender. Far from the horizon, photons stream outward easily, their motion tracing the smooth geometry of space. But as they draw near the black hole, the curvature deepens until light itself bends back upon its path. Some photons spiral inward and vanish. Others skim the surface, trapped in orbits that balance perfectly on the edge of eternity. This delicate boundary, known as the photon sphere, lies just beyond the event horizon. It is the place where gravity is so strong that light can circle the black hole indefinitely. To an outside observer, these photons form a glowing ring around darkness, the luminous halo seen in the image of the supermassive black hole in the galaxy Messier 87. What we call the shadow of the black hole is not the object itself, but the outline of this orbiting light. The photon sphere is the stage on which light performs its final act, before disappearing into the abyss. To understand how this happens, we must recall that in Einstein's theory, Light always travels at the same speed through space-time. It does not slow as it nears the black hole. Instead, space-time itself bends so steeply that the straightest possible path loops back on itself. The photon is still moving forward, yet its future now leads in a circle. Gravity has not changed its speed. It has changed what it means to move straight. At the precise radius of the photon sphere, the orbit is unstable. A tiny nudge inward, and the photon plunges past the horizon. A tiny nudge outward, and it escapes to infinity. This instability gives the black hole's edge its sharp definition. Light does not fade gradually, it is either captured or released. The photon sphere marks the knife edge between visibility and oblivion. As matter falls toward the horizon, it emits light that bends, twists, and lingers near this sphere before escaping. To a distant telescope, this light appears delayed, distorted, and magnified. It creates multiple images of the same event, layered upon one another like echoes of time. Some photons take longer routes, looping the black hole several times before escaping. They carry the same story told at different speeds. A gravitational echo that stretches the meaning of now. To the falling traveler, these effects are invisible. Their view of the universe above grows narrower, the light of the stars concentrated into a ring that brightens as it shrinks. Each photon they see is one that has bent around the black hole multiple times before reaching them. The universe seems to fold inward, the sky becoming a tunnel of light. Beyond that tunnel lies darkness absolute, the region from which no photon can ever emerge. The event horizon is not a surface in the usual sense. It is a light-like boundary, a place where all possible future paths for light turn inward. A photon emitted at that surface remains there, forever, neither escaping nor falling further in. It is frozen, not by stasis, but by geometry. From our perspective, this creates the illusion of a surface of light that never moves, a skin of frozen radiation, marking the border of reality. To the outside universe, every photon that tries to escape from just above the horizon is stretched into infinite redshift. Its wavelength becomes so long that it no longer carries energy. This is why the black hole appears black. The light has not vanished, it has been slowed into stillness. Time for that light, as seen from afar, has ceased. Yet in the deeper geometry, this stillness is motion. The event horizon is a null surface, meaning that every point upon it moves at the speed of light through space-time. It is not static, it is a flowing boundary that always moves forward in time. The light that defines it is not held there against its will. It is part of the horizon itself, woven into its structure. The black hole's surface is therefore made of light, though light that can never be seen. If we imagine the event horizon as a kind of frozen river, then space-time outside it flows slowly, while space-time inside it plunges downward faster than light can swim. The surface between them is the point of no return. Any particle or photon reaching that current is swept inward, carried toward the singularity, not by force but by the flow of reality itself. The horizon is not a trap in space, it is a trap in time. Astronomers observing black holes see this interplay of light and geometry written across the cosmos. When a star or disk of gas swirls around a black hole, its light becomes a probe of the curvature. Some photons escape directly, others are bent around once, twice, even several times before reaching us. These multiple paths create rings of brightness, each corresponding to a different number of loops around the black hole. The result is the image we now call the black hole's shadow, a dark circle surrounded by light that has nearly escaped oblivion. The symmetry of this image reveals the perfection of Einstein's equations. Every photon that reaches our telescopes carries information about the structure of spacetime itself. The brightness and shape of the ring tell us the mass and spin of the black hole, the way it drags spacetime along as it rotates, and the depth of the gravitational well. Even the darkness at the center tells a story. It marks the region where light has been delayed into infinity. But not all black holes are the same. When a black hole spins, its horizon and photon sphere twist along with it. The rotation drags space-time around, a phenomenon called frame dragging. In such a system, photons can orbit in complex, swirling paths, some co-rotating with the black hole's spin, others moving against it. The light from these paths produces an asymmetric shadow, a warped ring that encodes the black hole's rotation. The universe has given us a way to read the motion of space-time, itself written in light that barely escaped. For the light that does not escape, its fate is timeless. Once it crosses the horizon, it becomes part of the black hole's history, no longer a signal, no longer a messenger. Its energy contributes to the mass of the black hole, deepening the curvature further. The light that once carried information about the world now becomes part of the structure that conceals it. This transition, light turning into geometry, marks one of the most profound boundaries in nature. It is where information becomes space-time, where the act of vanishing creates the shape of what remains. The horizon is not merely where light fails to escape, it is where light becomes the black hole itself. The photons that hover at the edge are the last witnesses of the universe outside. They linger infinitely long in the stretched fabric of time, forever on the verge of escape. To us, they define the black hole's appearance. To themselves, if such a notion could exist, they are neither moving nor still. They are the frozen motion of space-time, the visible edge of the invisible. This interplay between light and gravity is not merely spectacle, it is the foundation of modern astrophysics. By studying how light bends, stretches, and vanishes near black holes, scientists map the shape of space-time itself. Each observation refines our understanding of how gravity works, how time slows, and how the universe hides its most violent transformations behind horizons of silence. In the end, the light that never escapes is not lost. It has become the very definition of the black hole's identity. Its absence shapes the image we see. Its struggle against gravity sculpts the ring of fire that reveals the unseen. The black hole is the darkness carved by the memory of light. And so, at the horizon, we find not the destruction of illumination, but its perfection. Light and gravity meet there in balance, their dance frozen at the edge of eternity. Beyond that edge, the story of time continues, but only inward. The next mystery lies not in what escapes, but in what remains. How the black hole's surface might hold the secrets of everything that has ever fallen within. At first glance, a black hole seems like the simplest object in the universe. It has no surface, no texture, no color, no detail. Once matter crosses the horizon, every trace of its identity disappears. All that remains is the mass, the spin, and the electric charge. To describe an entire star or a lifetime of falling material with only 3 numbers seems almost sacrilegious. Yet this is the prediction of general relativity. Black holes have no hair, as physicists say. They are perfect, featureless geometry. But this simplicity conceals a deep paradox, one that challenges the very foundation of physics. When matter falls into a black hole, it carries with it information, the specific arrangement of particles, the quantum state of its atoms, the history of its energy. According to the laws of quantum mechanics, this information cannot be destroyed. The evolution of any system is reversible in principle. But in a black hole, that rule appears to break. Once the matter crosses the horizon, the information seems lost forever. The black hole radiates nothing but silence. When it finally evaporates through the slow whisper of Hawking radiation, what remains of the information that once fell in? If it is gone, then the laws of quantum physics have been violated. This is the information paradox, one of the greatest puzzles in all of science. It began with Stephen Hawking's discovery in the 1970s that black holes are not perfectly black. Through the subtle interplay of quantum fields near the event horizon, pairs of particles constantly form and annihilate in the vacuum. Occasionally, one of these pairs is split apart by gravity. one particle falls in, the other escapes. To an observer far away, the escaping particle appears as radiation emitted by the black hole. This process continues endlessly, causing the black hole to lose mass over immense timescales. Eventually, it may evaporate entirely. Hawking's calculation was revolutionary, but it carried a troubling implication. The radiation emitted by the black hole seemed to be completely random, carrying no imprint of the matter that formed it. If that were true, then when the black hole vanished, all the information that had fallen in would vanish too. The universe would lose data permanently, and with it, the principle of unitarity, the idea that information is preserved in all physical processes. Quantum mechanics would crumble at the feet of gravity. For decades, physicists wrestled with this contradiction. On one side stood the unyielding precision of quantum theory. On the other, the elegant geometry of general relativity. Both could not be true in their current forms, and yet both had passed every test ever devised. Somewhere at the horizon, reality itself was split in two. As the debate unfolded, new ideas began to emerge. One of the most profound was the holographic principle. It proposes that all the information contained within a region of space can be described entirely by data encoded on its boundary. In the case of a black hole, this means that everything that has ever fallen inside might be stored not within the singularity, but on the surface of the event horizon itself. The horizon would then act as a cosmic hologram, preserving information in a two-dimensional form that projects the illusion of a three-dimensional interior. This principle finds support in the mathematics of quantum gravity and in the study of entropy. The entropy of a black hole, a measure of the number of possible internal configurations, was discovered to be proportional not to its volume, but to the area of its horizon. This was a shocking insight. For ordinary objects, entropy scales with volume. For black holes, it scales with surface area. This means that the horizon is not a passive boundary. It is an active participant in the universe's bookkeeping of information. In this view, the event horizon becomes a kind of storage device encoding every particle, every photon, every quantum state that has crossed it. From the outside, the black hole appears simple, but beneath that simplicity lies an unimaginable density of information. The surface area, measured in Planck units, defines the maximum information the black hole can hold. Each square of that minuscule scale, far smaller than an atom, represents a single bit of information. The black hole's smooth, dark face hides the most complex data structure in the cosmos. This idea links to an even deeper insight. The nature of space-time itself might be holographic. The universe could be a projection of information stored on a distant boundary, much as a three-dimensional image emerges from a two-dimensional hologram. In that case, black holes are not anomalies. They are the most direct evidence of the universe's underlying code. Their horizons are not walls, but mirrors, reflecting the quantum information that defines reality. If the horizon encodes everything that falls within, then Hawking radiation may not be random after all. The escaping particles might carry subtle correlations that, taken together, preserve the information content of the black hole. To an observer with infinite patience and perfect instruments, the radiation would reveal the complete story of what fell in. The process would be unimaginably slow, the information scrambled beyond recognition, but it would not be lost. In this way, quantum mechanics could survive intact, and the paradox could dissolve. However, this raises another mystery. How does information escape from a region that, by definition, traps everything? The answer may lie in the quantum nature of space-time itself. At the Planck scale, the horizon is not smooth but fluctuating, a frothing sea of microscopic geometry. Virtual particles, quantum entanglement, and space-time curvature intertwine in ways our classical intuition cannot grasp. The horizon is not a fixed surface, but a dynamic, quantum object, a membrane of information at the boundary of causality. This membrane may allow information to leak outward in subtle ways, encoded in the correlations of Hawking radiation. Each particle that escapes carries a tiny fragment of the black hole's hidden history. Over vast stretches of time, 10 to the power of 67 years or more, the entire content of the black hole could, in theory, be released back into the universe. To the naked eye, this process is invisible, but in principle, the universe never forgets. If this is true, then the horizon is not merely where time stops. It is where the deepest memory of the cosmos resides. Every atom, every star, every photon that has ever fallen in remains written upon it, in a script of geometry and quantum entanglement. The black hole becomes not a destroyer of information, but its most perfect archivist. The implications stretch far beyond black holes. If space-time itself is holographic, then the flow of time, the motion of matter, even the expansion of the universe may be emergent properties of information processing on a cosmic scale. Gravity, in this view, is not a fundamental force, but a thermodynamic phenomenon arising from the flow of information. The horizon is where that flow halts, where entropy reaches its limit, and where time itself appears to stop. The information problem, then, may be not a crisis, but a clue. It points to a deeper unity between quantum mechanics and gravity, one that transcends both. The horizon's secret is that reality may not be built from matter and energy, but from information and geometry intertwined. What we call time could be the unfolding of that information, and what we call space could be the network of relationships that binds it. When we gaze at a black hole, we are looking at the universe's most profound paradox made manifest, a place where information vanishes and yet is preserved, where light ends and yet defines the shape of what remains, where time stops and yet continues within. The horizon is the mirror of existence, showing us not destruction, but transformation, the boundary where the universe rewrites itself. At the edge of the black hole's horizon, the laws of physics converge. Geometry, energy, and information, once thought to belong to separate domains, begin to speak the same language. It was once believed that gravity was distinct from thermodynamics, that the curvature of space-time and the motion of heat shared no common ground. But in 1995, the physicist Ted Jacobson made a discovery that would change that view forever. He showed that Einstein's field equations, the very heart of general relativity, could be derived from the laws of thermodynamics. The idea seems almost impossible. How could the bending of space-time, the motion of planets, and the slowing of time all emerge from something as familiar as heat flow? Yet the connection is undeniable. In thermodynamics, heat always flows from regions of higher temperature to lower temperature, and entropy, the measure of disorder, always increases. In gravity, energy curves space-time, and that curvature defines the motion of everything within it. Jacobson realized that if one assumes every local patch of space-time has a horizon, and that the entropy associated with that horizon is proportional to its area, then the Einstein equations follow naturally. Gravity, in this view, is not fundamental. It is the manifestation of space-time's thermodynamic balance. To understand this, imagine standing near the event horizon. To you, the surface feels cold, silent, utterly dark. Yet from the perspective of quantum fields, that surface radiates energy. This is Hawking radiation, the faint emission caused by quantum fluctuations near the horizon. The black hole has a temperature, one inversely proportional to its mass. A massive black hole radiates little, while a small one radiates intensely. The horizon behaves like a thermal system, complete with entropy and temperature. This realization turns the black hole from an abyss into a physical object governed by the same rules that describe boiling water or the glow of a star. The event horizon possesses entropy proportional to its area, given by a simple formula: 1/4 of its surface area divided by the Planck constant and the square of the speed of light. This relationship, discovered by Jacob Bekenstein and Stephen Hawking, suggests that each tiny patch of the horizon carries a bit of information, the fundamental unit of entropy. The black hole's area is therefore a measure of its information content. When matter falls in, the area increases. When the black hole radiates away mass, the area shrinks. The second law of thermodynamics is preserved, for the total entropy of the universe, black hole plus radiation, always rises. In this thermodynamic picture, time itself takes on new meaning. The flow of time is tied to the increase of entropy. Wherever entropy rises, time moves forward. The black hole's horizon, with its immense entropy, marks the ultimate arrow of time. Outside it, time flows according to the gradual spread of disorder. At the horizon, that disorder reaches its maximum, and the flow of time slows to stillness. This perspective suggests that gravity and time are two sides of the same coin. When mass curves space-time, it also creates a gradient of time flow, a difference in the rate at which entropy evolves. The deeper you go into a gravitational well, the slower time runs, because the entropy of that region has already increased. The horizon is the endpoint of this process, where entropy reaches its limit and time ceases to advance. The connection between entropy and time becomes even more striking when we consider acceleration. If you accelerate through space, a horizon appears behind you, a region of space-time from which signals can no longer reach you. To you, that horizon glows faintly with thermal radiation, its temperature proportional to your acceleration. This is known as the Unruh effect. The faster you accelerate, the hotter the radiation becomes. Once again, temperature, entropy, and geometry intertwine. The very act of defining a horizon creates thermodynamics, and with it, the experience of time's passage. This tells us that time might not be a fundamental property of the universe at all. It may emerge from entropy, from the collective behavior of microscopic degrees of freedom that make up space-time. In this sense, the flow of time is the universe's way of balancing its own energy. The future exists because the universe seeks equilibrium. The black hole horizon, as the most extreme entropy surface imaginable, is where this balance reaches perfection. If gravity is indeed the thermodynamics of space-time, then every curved surface, every region of accelerated motion, carries a temperature and entropy of its own. The universe becomes a vast network of interacting horizons, each one defining its own arrow of time. The smooth, continuous geometry described by Einstein's equations is simply the large-scale behavior of an underlying statistical system, a cosmic fluid made of information. In this framework, space and time are not the stage upon which matter acts. They are emergent phenomena arising from information flow. The temperature of a horizon tells us how fast information is being exchanged between regions of space-time. The curvature tells us how that flow changes with energy. The Einstein equations become, in essence, the thermodynamic equation of state for the universe. This thermodynamic interpretation also explains why time has direction. On the smallest scales, the laws of physics are reversible. A film of two colliding particles looks the same played backward, but entropy gives time its arrow. It defines a direction in which events unfold, from order to disorder, from simplicity to complexity. The black hole horizon, with its vast entropy, is the cosmic terminus of this arrow. Beyond it, the notion of later loses meaning, for no process can further increase entropy once maximum disorder has been achieved. Thus, the slowing of time near a black hole is not merely a geometric effect, it is thermodynamic. As entropy approaches its limit, the drive toward equilibrium ceases. The flow of time, inseparable from that drive, slows and finally halts at the horizon. From the outside, the black hole is timeless. From the inside, time flows until it runs out at the singularity. Both views are united by the same principle. Entropy defines time, and gravity defines entropy. Some physicists have extended this idea even further, suggesting that space-time itself might arise from quantum entanglement, the statistical correlations between particles. In this picture, the geometry of the universe is woven from networks of information, and the smooth fabric of space-time emerges when these networks behave thermodynamically. The event horizon is the place where these correlations are severed, where entanglement ends and time stops. If this is true, then the black hole is not merely a cosmic graveyard, but the most fundamental laboratory for understanding existence. Its horizon is the physical embodiment of the laws that govern everything: geometry, energy, entropy, and time. The study of black holes, once a curiosity, has become the key to uniting the two great pillars of physics, relativity and quantum mechanics. In the final analysis, the thermodynamics of gravity reveals something profoundly beautiful. The universe is self-consistent. The flow of heat, the curvature of space-time, and the march of time all express the same principle: the tendency of nature toward equilibrium. When we fall toward a black hole, we are not falling into chaos, but into the purest expression of order, where time, energy, and geometry align perfectly. The horizon, then, is not merely where time stops, it is where time is defined. It is the universe's clock face, marking the balance between what can happen and what cannot. To understand it is to understand why time moves forward, why the universe expands, and why reality exists at all. The event horizon marks the end of our visible universe, yet mathematics insists that this need not be the end of all possible paths. When Einstein's equations are extended beyond the familiar black hole solution, they reveal hidden symmetries, mirror reflections of space-time that suggest the existence of other realms. From those symmetries arise two astonishing possibilities: wormholes, the tunnels that could connect distant parts of the cosmos, and white holes, the time-reversed twins of black holes that expel rather than consume. In 1935, Albert Einstein and Nathan Rosen discovered that the equations describing a non-rotating black hole could be mirrored to form a bridge between two regions of space-time. This structure, now known as the Einstein-Rosen bridge, is the earliest mathematical description of a wormhole. To visualize it, imagine taking a two-dimensional sheet of space and folding it so that two distant points touch. A tunnel appears between them, short in distance but vast in gravitational depth. Objects entering one mouth of the bridge could, in principle, emerge from the other. The horizon of a black hole would then not be an ending, but an entrance. Yet nature is not so forgiving. The Einstein-Rosen bridge is unstable. It pinches off before anything can pass through. The moment an object attempts to enter, the tunnel collapses faster than light can traverse it. Time and geometry conspire to preserve causality, sealing the passage before it can become a corridor between universes. The mathematics shows that the bridge exists only as a fleeting connection, open for an instant in the coordinates of the external universe. For all practical purposes, it is a dream, a mirage made of geometry. Still, the idea refused to die. Decades later, physicists began to explore new versions of these bridges that might remain open. The key was energy. In ordinary matter, gravity always attracts. Space-time always curves inward. But if negative energy, something that repels instead of attracts, could be harnessed, it might counteract the natural tendency of the bridge to collapse. Quantum field theory allows for such negative energies in small amounts, arising from vacuum fluctuations and the Casimir effect. These exotic energies, if arranged correctly, could stabilize a wormhole long enough to permit passage. In theory, a traversable wormhole would be the ultimate defiance of gravity's tyranny. It would allow instant travel between distant regions of space and even between different moments in time. Enter one mouth and emerge light years away, or perhaps centuries earlier. The equations permit such structures, but only barely. The energy required would be immense, the control over quantum fields beyond our current technology. And even if such a wormhole could exist, the paradoxes of time travel would test the consistency of the universe itself. White holes, too, arise naturally from Einstein's equations. If a black hole is a region where nothing can escape, a white hole is its mirror image, a region where nothing can enter. To an external observer, it would appear as an explosion frozen in time, matter and light, eternally flowing outward but never inward. In the time-reversed version of a black hole's geometry, the singularity becomes a source rather than a sink. Such objects would be extraordinarily unstable, likely impossible to form under normal conditions. Yet they remind us that the laws of physics, when followed to their logical conclusion, possess a strange kind of symmetry. Every collapse can be mirrored by an expansion, every end by a beginning. Some have speculated that the Big Bang itself might resemble a white hole. The universe could be the ultimate outflow of matter and energy from a singularity, not into a pre-existing space, but into space itself as it unfolds. In this view, the black holes scattered throughout the cosmos could be seeds of new universes, each horizon concealing its own Big Bang beyond reach. The geometry allows it, though the evidence remains hidden behind the veil of the event horizon. In the realm of quantum gravity, the distinction between black holes, white holes, and wormholes begins to blur. The quantum foam of space-time at the smallest scales may constantly create and destroy microscopic wormholes, ephemeral tunnels that connect distant points for fractions of a second. These quantum fluctuations could be the foundation upon which space-time itself is built, a network of connections that gives rise to the smooth geometry we observe. If horizons can connect rather than isolate, then the universe might be far more interconnected than we imagine. The event horizon would not be an end, but a membrane linking two sides of a greater whole. A particle falling into a black hole in one region might reappear through a white hole in another, its information preserved in the curvature that binds them. In this sense, the horizon becomes both a wall and a bridge, depending on how we define time. Quantum mechanics complicates the picture further. In the holographic view, the interior of a black hole is encoded on its surface, but that surface could be entangled with another elsewhere in the universe. This leads to the Earphones conjecture, proposed by Juan Maldacena and Leonard Susskind, suggesting that every pair of entangled particles is connected by a microscopic wormhole, an Einstein-Rosen bridge on the quantum scale. If true, entanglement and geometry are not separate phenomena, but two descriptions of the same underlying reality. The universe would then be a vast web of wormholes connecting all points through the invisible threads of quantum information. The implications are staggering. Gravity, space-time, and even causality might emerge from the collective behavior of these quantum connections. The smooth fabric of the cosmos could be the macroscopic appearance of a deeper, woven structure, where information and geometry are indistinguishable. The horizon, in this light, becomes not an edge, but a phase boundary between two ways of describing reality, one classical, one quantum. Although no traversable wormhole or white hole has ever been observed, their mathematical possibility forces us to reconsider what the horizon truly means. It may not be the ultimate barrier, but a mirror showing us the symmetry of the universe's laws. Time may not always flow in one direction. In certain geometries, it could loop, connect, or even reverse, depending on how space-time folds upon itself. The more deeply we explore these ideas, the clearer it becomes that horizons are not merely regions of space. They are manifestations of time's structure. A wormhole bends not only distance but duration, linking moments as well as locations. A white hole represents the rebirth of time from the ashes of its death. The horizon, seen through the lens of quantum gravity, is a dynamic, living interface where the universe reinvents itself. Perhaps one day, when our understanding of quantum gravity matures, we will see that every horizon is both an ending and a beginning, every singularity, both a collapse and an emergence. The geometry that traps light may also be the mechanism that creates it elsewhere. Time, space, and information may not be confined to one side or the other, but circulate through the cosmic fabric in patterns yet unseen. For now, wormholes and white holes remain the poetry of mathematics, beautiful, haunting, and elusive. They remind us that the universe's laws possess a symmetry that transcends our experience, that the same equations describing the fall into darkness can also describe the flight into light. The horizon is both a wall and a bridge, both death and rebirth, depending on how we choose to read time's equation. At the end of all gravity's stories lies a single question. What does it mean for time to stop? The black hole's horizon, the singularity, the fading of light, all of them point toward a truth that seems impossible. Time, the measure of all change, can reach a place where it no longer flows. It is not destroyed by force or pressure, but by the structure of reality itself. When gravity becomes infinite, when curvature folds space-time into its own shadow, the very concept of later ceases to exist. For an observer far away, this ending is never seen. Matter falling into a black hole appears to slow forever, its light stretching into red, its motions frozen at the edge of visibility. From that distant perspective, the universe's clocks continue to tick, but the ones near the horizon stop. The black hole becomes a monument to halted time, a sphere of stillness surrounded by the flow of eternity. For the traveler who falls, the story is very different. They do not witness the freezing of their own time. Their clocks keep running, their heart still beats, their thoughts still unfold. To them, time flows unbroken, carrying them inevitably inward. They pass through the horizon without fanfare, unaware that they have crossed the ultimate divide. Their descent continues until they reach the singularity, the end not of space, but of the future itself. The duality between these two views is the essence of the horizon's mystery. Both are true, yet they cannot coexist within a single frame of reference. For the outside universe, the fall never completes. For the infalling traveler, it ends in finite time. Time, then, is not absolute. It is woven differently for every observer, stitched together by gravity's hand. The universe does not share a single clock. It contains a multitude, each marking its own rhythm, each defining its own boundary of existence. The singularity represents the ultimate consequence of this divergence. It is the point where every timeline inside the horizon converges. To approach it is to move not through space, but through the last remaining instance of time. There is no path that avoids it, no way to linger or turn back. All futures end there. The singularity is not somewhere. It is the final moment in every possible sequence of events. Yet, even as time ends within, the black hole itself evolves. Outside observers see its horizon grow, shrink, and glow faintly with hawking radiation. The black hole ages. Over unthinkable periods, 10 to the power of 67 years or more. It evaporates, releasing the energy it once consumed. Eventually, it disappears, leaving behind a faint mist of particles. The universe continues, but the interior that once existed has been erased from causal contact. The end of time for those who fell has been translated into the passage of time for everything else. This paradox, time ending in one place while continuing elsewhere, forces us to confront the limits of understanding. Our physics can describe what happens as we approach the singularity, but not what lies beyond it. The equations stop making sense. Infinity appears not as a number, but as a failure of language. The singularity marks the point where the geometry of space-time can no longer be drawn, where our definitions of before and after lose coherence. It is not a wall that blocks knowledge, it is the edge of what knowledge means. Some theories suggest that time might not truly end there. Quantum gravity may smooth out the singularity, replacing it with a region of extreme but finite curvature. In such models, space-time could bounce, giving birth to a new domain on the other side, a new universe, expanding into its own future. If so, black holes might be the engines of cosmic rebirth, each horizon concealing another Big Bang beyond. Our universe could be one among countless generations, each born from the ashes of the last. Others propose that time itself may emerge from deeper principles. If space-time is built from quantum entanglement, then the singularity is simply the point where entanglement ends. Beyond it lies not another universe, but the absence of relationship, the place where information no longer connects. In that sense, the end of time is not destruction, but separation, the dissolution of the network that gives meaning to motion and change. The notion that time can end challenges everything we believe about existence. Our minds are built to think in sequence, to imagine past, present, and future as an unbroken line. But the universe is not obligated to follow our intuition. In relativity, time is a coordinate, one dimension among others. It can bend, stretch, or halt, depending on geometry. In quantum theory, time is not even fundamental. It may emerge from the collective behavior of systems. The black hole reveals this truth in its most dramatic form. Time is local, and it can die. If we could watch a clock fall into a black hole, we would see it slow, fade, and freeze. We would never see its final tick. But for the clock itself, that tick would arrive swiftly, marking the end of all moments. The contradiction is only apparent because time is not shared between observers. Each world line has its own measure of duration, its own boundary of existence. The horizon is the seam where these measures diverge beyond repair. The death of time within the black hole mirrors the death of time at the edge of the universe. In the far future, when stars have burned out and galaxies drift apart, expansion will stretch space so greatly that no light can bridge the distance between worlds. The cosmos will fade into cold darkness, approaching thermodynamic equilibrium. Entropy will reach its maximum, and with it, the arrow of time will lose direction. The universe will become timeless once more, not through collapse, but through stillness. In this way, the black hole is a microcosm of the universe's fate. Both begin in fire and end in silence. Both transform energy into entropy until there is no distinction between change and rest. The horizon that surrounds a black hole is the same kind of horizon that surrounds the entire cosmos, the boundary beyond which no signal returns. The end of time within and the end of time without are reflections of the same law. Philosophically, this raises a haunting question. If time can end, does it truly exist? Or is it merely the shadow of change, the illusion created by entropy's rise? If time is tied to information, then perhaps it is not fundamental at all. It may be a bookkeeping system for the universe's memory, a measure of how far order has decayed into disorder. When that process completes, when there is nothing left to change, time's purpose is fulfilled. Yet from within that silence, something extraordinary may persist. The information that defines the universe might never vanish, only rearrange. Quantum theory forbids the loss of information. The end of time could therefore be an illusion caused by our limited perception, a boundary that hides a deeper layer of reality where time is replaced by something else. Perhaps a static network of relationships, perhaps a higher dimensional order where the entire history of the universe exists at once. At the edge of gravity's grip, time slows, bends, and finally breaks. For those who remain outside, the clock continues to tick. For those who cross the horizon, the moment never ends. The gravity horizon is not the end of space. It is the end of meaning for the word before. The universe, in its vast indifference, allows both truths to stand. Time flows and time ends. Light escapes and light freezes. Existence moves forward, even as parts of it are sealed in eternal stillness. The black hole is the ultimate mirror, showing us that what we call reality is not one thing but many, stitched together by geometry, divided by perspective, and bound by the gentle tyranny of entropy. In the final silence beyond the horizon, there is no past, no future, no waiting. There is only the end of the question itself. What we call the death of time is simply the moment when time has nothing left to measure. And in that moment, perhaps, the universe becomes what it always was, an eternal, changeless whole, where every event that ever was or will be already exists, complete and infinite, waiting only to be seen.